Good afternoon and welcome to MAE 209 Probability and Statistics. My name is Richard Kohar and this is lecture 23. Hopefully the sound is okay and we can start. Just double check in the chat. Sound check. Okay, it looks good. So we're going to be talking about point estimators, and these are very common in statistical inference. Usually in statistics, we are trying to infer the characteristics of the entire population from a sample. So you can think of this, again, it's inference. So again, we're starting with a very small thing and trying to extrapolate it to the entire population. And we can also, again, remember or go back to our discussion from the first week of lectures when we were talking about a population versus a sample. And these notes are been posted on Moodle. There's the fill in the blanks version, so if you would like to download and follow along and fill it in, you're welcome to do that as well. I will post the filled in version afterwards. Okay, so the goal in this section is to describe a population using some probability distribution, and what we have to do is estimate those parameters, right, from the observed sample data. So for instance, like let's think of, we have the lifetime of a rechargeable battery. It's in some sort of communication device, some sort of mobile phone, GPS, situational awareness system. And you want to try to say, describe that using a normal distribution. Okay, well, in a normal distribution, there's two parameters. First of all, in the chat, what are those two parameters of a normal distribution? There's two parameters in yes and no. So just as the question, what are the two parameters of a normal distribution? Just in the chat, what would you say? Oh, someone's even put in the Greek letters. Yes. So for our two parameters, we have is mu and sigma squared. And we usually had said that like this. And we would say like x is a random variable that follows the normal distribution with. Now, I was pretty careful about, well, sometimes I would say it, but that this is the expected value. And over here is the variance. And again, we had gone through this, but just as a little refresher, we have some sort of like bell-like curve here at the mode is also the expected value mu, and at the point of inflection is one standard deviation. Now, some people are saying mean, and there's a reason why I kind of avoid saying it when I talk about the parameters of a normal distribution. We'll get to that in a second. So, suppose you want to estimate the expected value parameter, and that's, in this case, it's mu. And you also have the data x1 is equal to 5, x2 is equal to 6.4, and x3 is equal to 4. How would you estimate the expected value parameter? So just in the chat, how would you estimate this? Average it out, that's good. And what we're going to use is the mean. We're going to use the arithmetic mean, right? So table A3. No, not A3. No, because what we need is we have this data here. So we're going to use x bar, and that is you can think of it as the average or the mean, and that is equal to, again, if we take the sum of all the variables and we divide it by n, which is the number that we have here. So what we have is 5 plus 6.4 plus 4, all divided by 3. So what does this equal? If you have a calculator handy, or let's see, 5 plus 6.4 plus 4 is 15.4, and then, okay, good. There's some people that will be checking what I've done. Yes, so let's round it just to 2 decimal places, 5.113 there. Okay. So this is what I'm going to say. Using the mean seems reasonable, and it's a plausible value of the expected value. So what I'm trying to say, it's a good guess to based upon the available sample information that we have to use that. So what I could say is that, you know, we could describe that battery life that we were talking about, the battery life of a rechargeable battery, by using that normal distribution, 5.13, and we don't have a variance at the moment. Okay, so you can understand where I'm going with this, that this is what the mean versus the expected value. So what did we just do? Is something in statistics is what we called an estimator. So let me just switch pages here. This is number 2. Okay. So we have a point estimate of a parameter, and we're going to use theta just to kind of be general. That's theta is a single number that can be regarded as a sensible value for theta. Now, again, what they're trying to do is that theta is some sort of parameter. So again, we're trying to estimate the parameter there, So we're trying to figure out a single value that can be regarded for that parameter. So again, it could have been mu or sigma. A point estimate is obtained by selecting a suitable statistic. We have a word here, statistic, and computing its value from the given data. The selected statistic is called the point estimator of theta. So what we had done in the previous one is we were trying to estimate what mu was. And so what we had done is we had used the mean. We had used the descriptive statistic, the mean, to come up with a value for mu. And what this is saying is that we had some data, we applied some calculation to it, and we got a value. And that's what we're using as our estimate for that parameter. So in this case, this is the point estimator. So this is the point estimator of mu. Okay. But notice that I used the word suitable statistic. And what is a statistic? You know, the average person on the street would say it's just some fact or some piece of data from a study, you know, that Quebec manufactures 77% of the world's maple syrup, or that the average weight of a Canadian male is like 84 kilograms. But that's not what we mean in math. We are a little bit more precise about it. And we say that a statistic is a quantity that is computed from values in a sample. So you can think of it as basically a statistic is a function. You have some data. So it's not a fact. It's not some sort of, trivia or data. It's a function. And so that there is some sort of information that gets passed into a function, and out comes a single real number. So again, a statistic is a quantity that is computed from values in a sample. And when a statistic is used for estimating a population parameter, like what we were doing with the battery, then we call that statistic an estimator. Okay? We had seen this in the first chapter. There was many descriptive statistics that we could use. We had the sample mean, we had the median, the mode, the variance, the standard deviation. So again, these were all things that we had seen, so you can look back to our previous chapters or previous lectures. So what I'm saying is we could have these descriptive statistics, again, with the mean, the median, the mode. These could be candidates for estimating parameters in our distributions. So let's jump over to page 3. Maybe I should just make one little remark. So in the battery example that we had done, the estimator used to obtain the point estimate of mu was x bar. And the point estimate of mu was 5.13. So if we had these 3 observed lifetimes had been instead some other values, we would just use again the mean. We could just change it. It's customary to use a symbol with a hat. So whenever we're trying to estimate the parameter, so it's not mu. So mu is not equal to the mean. Instead, this is the estimate. So we say, when we put the little hat on top of it, that this is the point estimator of mu is the sample mean x bar. And so you could also say that this we could also finish off, therefore, the point estimate of mu is 5.13. Now there should be some sort of hours or some sort of units here, so we'll say hours okay. So now what we'll do is we'll go to the third page here, a point estimator. So we say a point estimator, so we have the parameter we're going to estimate, so it's theta hat, is said to be an unbiased estimator of the parameter we're trying to look at. So let's say theta. We say it's an unbiased estimator if the expected value of the point estimator is equal to theta. So again, we expect the point estimator to be equal to the true value. So if we go back to our previous example here, what I'm trying to say here is that we hope that an unbiased estimator, that in this case, that the expected value of mu is equal to mu. Okay. So that's what we're saying here. For every possible value of theta, if the point estimator is not unbiased, then what we do is we look at the difference of it. So if the difference is called the bias of theta. So in other words, you could see this as that if it's equal to 0, it's unbiased. And if it's not equal to 0, then it's biased. So what does this mean? In other words, it is an unbiased estimator if its probability distribution is always centered around the true value of the parameter. So this is what we are worried about, is that, sure, we could have, let's say, this is what the true distribution looks like. What we hope for is that the mu hat is also the same. But this isn't always the case, depending on what kind of statistic you're using as your point estimator. This would be unbiased. Over here, what you could have is you have your distribution, and again we'll have our mu here. This is the true value, but instead it could be shifted. So this over here would be now my mu hat. And what they say here is the difference between here is the bias. Now, you might think that it's necessary to know the true value of it to see if the point estimator is biased or not, but that's not usually the case, because unbiasedness is a general property of the estimator's sampling distribution, and that's where it's centered, and it's typically not dependent on any particular parameter values. So what we're going to do is, so that's kind of the question. Don't you need to know what theta is to determine if your point estimator is biased? So to rebut this question, we have this proposition here. So here's the proposition. When x is a binomial, discrete, random variable with parameters n and p. So what this is saying is that if x follows a binomial distribution, it has n and p. N again is the number of trials, p is the probability of success. The sample proportion, so we're going to say p hat, and that's our estimator. Is an unbiased estimator. So we can actually show this. Now it requires us to remember our properties of expected values. So again, we'll have to remember expected values. So if I have a constant times a random variable, it's equal to the constant times the expected value of x. If I have two random variables, say x and y, that is equal to this expected value of x plus the expected value of y. Okay. So what we're going to do is we're going to look at the expected value of the estimator, p, and we're told what it is. So we'll replace that. We have x over n. Now n is a constant. That's something that doesn't change. So I can actually bring that out in front because, again, it's a constant. Now, in the chat, what is the expected value of a binomial random variable? So what's that value? What's the value of a binomial random variable with parameters n and p? Anyone in the chat? That's right, it's n times p. So what we have then is 1 over n times n p. These are canceled, and I'm left with p. So therefore, the expected value of the point estimator is equal to p. Oh, and for the person who said mu, again, we're working with a binomial random variable. So because of that, the expected value is equal to np. And remember that the variance is equal to np 1 minus p. So yes, this is a proof. It's very simple. Again, it's just knowing that you have to look at the expectation of your estimator. Again, we defined it as x over n. We had to use our knowledge that since 1 over n is a constant, we can bring that out in front. We needed to remember that the expected value of x for a binomial random variable is np. Then it simplifies by canceling out the n's, and we're left with p. Okay, so moving on to number 4. Page 4. We need to remember what the sample, or the formula for the sample variance is. So let's see if I remember this right. So we had 1 over n minus 1, and then we're going to sum it, right, from, take the distance squared and over here that is the mean, so again that is equal to 1 over n like that. Now notice, why did we need to divide by n minus 1? Again, this was the sample variance instead of n. Now, I had said in lecture 3, page 3, that it is because we wanted an unbiased estimator. Now, probably it didn't mean anything at the time, but now that we have our definition of what an unbiased estimator is, what that means is that we expect that the expected value of s squared should equal sigma squared. So, that's what we're going to do. We have our proposition. We have a random sample. So notice that these are capital letters. These are random variables. So we have x1, x2, x all the way up to xn. So again, those are random variables. And then if we have a collection of them, we'll say that it's a random sample. And in statistics, what we usually do is we have capital letters like x and y for the random variables. And in statistics, for the values, they'll have values, or in statistics, they'll say realizations. Because there's actual values, they'll use like little x and little y. So again, we don't know what the values are. So they're just some random collection of random variables from a distribution, and we know what the expected value is. It's mu, and we're going to say the variance is sigma squared. So we know then for sure what those values are. So you can think of that as the population parameter, and the estimator of sigma squared, so we have the little hat on top here, is equal to big S squared, and we have our sums of differences between the value and x, and we divide that by n minus 1. Oops. And I forgot the squared here. Right, we wanted the squared distance. So this is how the proof will go. In the couple of lectures, we saw that we could rewrite s squared as 1 over n minus 1, and that we can take the summation of xi squared minus this was kind of the formula we had used for calculating the sample variance. Okay, so this is the formula. So now what we need to do is to show that this estimator is unbiased. I need to take the expectation and hopefully that it equals then sigma squared at the end. So what I should I'll write this out because it's to show s squared is unbiased. The expected value must equal sigma squared. Oops. Okay, so I'll just start on another page here. So I have my s squared. And what I need to do is apply the expected value. So I'll my expectation on both sides. So feel free to work this out as I'm working through this. Then the next thing is I'm going to apply the expected value or the expectation to each of these. So again, the 1 over n minus 1 is a constant, so I can bring that out in front. And so I'm left with this. Okay, so again, all I did was I brought this out in front. Then the next thing I can do is I'm going to apply the expectation to each of these terms. And the other thing is, okay, so okay, same thing here. I can bring that out front. I dropped a squared out here, so that's important. Then the next thing I can do is what I'm going to do is I'm going to exchange my expectation and the summation here. So again, what I can do in this part right here, remember that the expected value of x plus y is equal to the expectation of x plus the expectation of y. So if I wanted to generalize that, the expected value of, say, a sum of random variables is equal to the sum of the expected value. Okay, so that's why I can bring that out in front. Now I can't quite apply it to this one because it's a summation then squared, so I can't do it like that yet. The next thing that we need to remember is that our formula for variance. So let me grab a different pen. So our variance, remember that we had v of x is equal to the expected value of x squared minus the expected value of x all squared. Then the other thing I can do is I can rearrange this so that I should be a little bit careful on my here. What I can do then is I'm going to rearrange that so that I get expectation of x squared is equal to v of x plus the expected value of x squared. So that's what I have right here. I have the expected value of x squared, and I know what v of x is because what we had stated, v of x was sigma squared, and the expected value was mu. So that was sigma squared plus mu squared. So that's what I'm going to put in here. And over here, what I have is v of, so I can treat this like a random variable. So I have v of the sum of xi squared. Oh no, not squared, because I need to follow this formula. Right, plus the expected value of the sum of xi this has to be all squared. Again, following that formula. Now this is the expectation of a constant, so I don't have to worry about those are just constants, and I'm going to be doing sigma squared plus mu squared. It's going to be times n. So what I have then is n times sigma squared plus mu squared. Over here, now each of the variance, we're going to just do, well, we know what that is. It's n times sigma squared minus, and over here is the expectation of the sum of xi. So again, that's mu, like n times, so again, n times mu, and that will be squared. So we're almost finished. So I'll have n sigma squared plus n mu squared. Then I'll have the n's here. Gotta be careful that I don't get rid of, what I'll be left with is sigma squared minus, and then I have n squared mu squared, so I'll just have mu squared no, sorry. Make sure that nobody says anything in the comments yet. It should be n. So then those cancel. I'm left with yes, someone got me Someone noticed it. Then, you can factor this out. You have 1 over n minus 1, so you could have sigma squared, and then what's left inside would be n minus 1. That cancels out, and we're left with sigma squared. So then as an exercise, what you should show is that okay, let's say that we're going to use our estimator. This is a different estimator. So instead of using n minus 1, we'll use just n. Show that it's biased. Now, just a small warning. I should make a little remark. So we saw that s squared is an unbiased estimator of sigma squared. However, if you take the square root, so just take s, is not an unbiased estimator of sigma. So again, this is fine for the unbiased estimator of the variance. But if you take the square root, it's not an unbiased estimator of the standard deviation. Okay. The reason for that is basically taking the square root messes up the unbiased property. That the expectation of some sort of square root is not equal the square root of the expectation. Okay, that's basically it. The next section is section 6.2, and that's when we start to get into methods of moments, but we'll be focusing on what's called MLE, and that is maximum likelihood estimators. There will be some practice problems for 6.1. I would say if you are trying to reinforce your learning, what I would say is that this exercise is a good one to start with. And I will post some questions through Moodle. But I would start with that one. Show that that is biased. And if you get stuck, see the textbook for a hint. Okay, this is right after the unbiased kind of the sample variance. Okay, thank you everyone for tuning in. If you have any questions, feel free to send me an email at my RMC account. Otherwise, enjoy the rest of your day. Take care, everyone.